Commencer? Yeah, you can sit here. Come here. And then you have you can charge.
Is this okay? But I am blocking the way.
This?
Yeah, this should be okay.
Yeah, it's okay, yeah. Because they see your screen.
Yeah. Oh yeah, people will see my screen. How stupid.
Yeah.
Okay.
So here's to show your face.
Yeah, I understand.
There are how many people
Stupid.
inside? Two?
No, I don't know.
There are only two participants.
And people might join from 9 because the sessions are from 9.
That is you. I know.
Yes, our mic.
It's new. Don't worry. So I think there are more people. Tu vas aller chercher les gens en bas? Bah, je vais présenter. Ah, est-ce que tu, où est-ce que tu veux présenter? Toi, j'ai pas prévu là. Non, c'est juste que faut que je vois, il y a tout le monde et tout. Et après, c'est une hamburger. Ah, ok, c'est pas de souci. Il faut juste que. Ok. On va commencer. Bon, tu peux faire. Bon. Non, je crois qu'ils vont encore trouver. Ça va? Ça va et vous? Ouais. T'es pas trop loin?
Non, ça va, j'ai trouvé. Mais ça fait longtemps que je suis pas venu par là, ça a beaucoup changé.
Ok, c'est vrai. Ça a changé entre temps.
Dur, très dur. Mais ça ira. Finalement, j'ai préparé des transparents parce que je savais pas si on va avoir vraiment des tableaux, mais suivant les questions, ça peut aider comme. Je sais pas si. Comment vous pensez? Il va y avoir du monde quand même sur place
Oui, je pense, ouais. Normalement, il y a 30 personnes.
30? Ouais.
J'espère qu'il va venir des choses. Pas désolé.
Et du coup, comment vous voulez qu'on fasse
Je vais vous donner un.
Ouais. C'est streamé par.
Ouais, on va mettre sur ce PC-là.
Ouais.
Il y a.
Ah, ouais. Oui. Je peux vous l'envoyer par. Je peux l'envoyer par. Non, mais je peux pas mettre là-dessus. Je vais peut-être mettre plutôt la. Au lieu que je mette une version PDF. Ah, pour un raccord. Sinon, je vous l'envoie par ligne ou par je sais pas. Parce que j'ai pas de.
Ok, bah sinon, c'est connecté par quelle adresse? Gmail? Ouais, ouais. Sur le Gmail, non. Il faut.
Sur un PDF.
C'est la machine.
Qui va diffuser?
Ouais, mais c'est pas notre machine.
Ah.
On peut pas brancher, c'est là?
Non, non, parce que je suis que en USB-C.
Ah, sinon, envoyez à moi.
Ouais.
Yes. So hello everybody. Hello. Welcome to the Qiskit Fun Fest at Université Paris-Saclay. My name is Min. I'm the team leader of the organization team. Today, we would like to welcome you to come with Université Paris-Saclay. And for the starting, I will introduce Dr. Poonham, who will present the opening section. Please, Poonham.
Thanks, Ben. Good morning, everyone. And on behalf of my amazing organizing team, I welcome you all to Qiskit Fall Fest 2025 here at Université Paris-Saclay. So, we know that quantum computing right now is transforming how we think about computation and complex systems. Inspired by pioneers like Richard Feynman, who envisioned using this quantum physics to simulate nature itself. Today, platforms like Qiskit and IBM Quantum bring this vision closer to reality to be used by everyone. So this week, we all come together to learn, experiment, and contribute to this global phenomena, and to join this community, to learn, to have fun. What better place than University Paris-Saclay? This year is doubly special because this year marks the 100th anniversary of quantum mechanics. It's a century since the birth of the theory of this quantum mechanics, which shaped the physics and technology. We are also celebrating two Nobel laureates from this university, Dr. Alan Aspect, who was awarded Nobel Prize in 2022 for quantum entanglement, and this very year, Dr. Michel Devoret for superconducting qubit. So I can't see a better place where we can hold this fest other than University Paris-Saclay. Let's talk a little bit about our host. This is one of the Europe's leading research universities. It's a home to 275 labs and over 9,000 researchers. This is the core of France's quantum Saclay ecosystem. Internationally recognized for physics, mathematics, computer science, biology, every branch. And it's a perfect host for bridging academic excellence, industry, collaboration, and education. So this 1 week, we have talks planned on various topics like quantum foundations, algorithm simulations, hardware and machine learning. We have speakers from leading universities all over the world and research lab worldwide, like University Paris-Saclay, University of Western Brittany, NYU Abu Dhabi, Rickens, CNRS, University of Oxford, and industry like IBM Quantum, Alice and Bob, Riverlane, HiQ, Quandela, C12, Entropica Lab, NTU, Planck, etc. For the day one, we also are conducting a lot of hands-on session. Our team has worked very hard for it. On day one, we have hands-on sessions on getting started with Qiskit and variational algorithm. Day two, we have noise error mitigation and quantum error correction. Day four, we have quantum machine learning. We also have panels and career guidance, panel discussion, career guidance. This feature companies like IBM Quantum, Unitary Foundation, Riverland, IQ, C12, and many more. A little bit about our participants. We have 200 plus participants from around the globe, from regions across the world, Asia, Europe, UK, Australia. We have students from various backgrounds, researchers, industry experts, professionals. We are all highly motivated to explore and contribute to this quantum computing community. Our focus in this 1 week would be to have discussions on quantum algorithm optimization, quantum machine learning, quantum error mitigation correction, bridging theory and real-world quantum application. And our focus is to empower participants to innovate and build in quantum technologies. A little bit about how the event will proceed. So our full program and the speaker list is there on our website. We also communicate all our announcements and every update on our Discord channel. Participants can post their questions and discussions during or even after the sessions. We'll try to respond to all of them. For the hands-on sessions, the notebooks and coding materials are available on our GitHub repository. The exercise follow the live sessions, and solutions will be posted on and discussed on Discord. This is our amazing organizing team. We come from various places, different backgrounds, but the goal is only one: to have a very nice 1 week of learning and have fun. A big shout out to our sponsors. We gratefully acknowledge the support of our sponsors: IBM Quantum, Université Paris-Saclay, Unitary Foundation, Alison Bob, Quandela, Aquara, Tropica Lab. It's for sponsoring and supporting hands-on workshops and hackathon. So once again, on behalf of everybody, I welcome you all to the Qiskit Fall Fest University Paris-Saclay edition. Let's engage, learn, and make most of this opportunity. We take this opportunity to connect with each other, collaborate, and create a wonderful memory. Let's enjoy the week and have fun. Thank you.
So there is actually a problem on a meeting.
Okay. I request them to come and.
It's recorded everywhere.
So where are the people online?
Right. Please, can you tell me if everything is okay? Can you hear well from online?
Yes, we hear you very well. Thanks.
Yes. So thank you. There only.
No, you can start with the.
All right. So thank you. Thank you again for joining us today. So please join me in welcome Professor Etienne Parizeau. Professor Etienne Parizeau is a senior French astrophysicist specializing in high-energy cosmic rays and particle astrophysics. A graduate of the École Normale Supérieure de Lyon, he's completed his PhD at Saclay, Institut de Physique Nucléaire d'Orsay, and has since held leading research roles at the CNRS and the APC laboratory in Paris. He has also played a key role in a major international cosmic ray projects and is an active science communicator who teaches quantum physics and relativity. Professor Etienne Parizeau was my bachelor professor when I was in Université Paris-Saclay. So thanks to his love and his passion, I'm here today to organize this beautiful event with you. And today will guide us through foundations of quantum mechanics. Please join Professor.
Hello, everyone. So happy to be here. Okay. We are uploading the presentation. I prepared some slides to help presenting the quantum physics foundations. Can you hear me well?
Yes, indeed. Thank you.
Okay, thank you. So we are now uploading the slides.
Slide.
Sorry, just one moment. The organizers are setting up.
Ouais.
Okay, we need to transfer the file on the right USB key. Will take 1 minute. Sorry about that. So I'm not sure what is the background of everyone online, and therefore I will ask you to don't hesitate to stop me if you have any question during the talk. I think it makes no sense that we don't interact and we get lost or in the oops, that's right. Or in the opposite case, you might know already so well what I'm going to tell, and then in that case, just tell me and we move forward. Yes, can you? I don't know where's the file. That's this one. Okay.
So, Etienne?
Yes. Okay. So let's start. Everybody sees the slides. Or no? Yes. Everybody's okay. Can you confirm that you hear me? I'm not so sure. I don't see anything. So.
We hear you fine. Thank you.
Okay, sorry. So now we can start. Yeah, so I'm going to present briefly the foundations of quantum physics, which are not so difficult, actually, not so many either. So I will go briefly through these different topics. First, I will recall what is our representation of the world to see what quantum physics brings compared to classical physics, actually not so many different. Then I will introduce the Stern and Gerlach experiment because I think it's the best way to enter the quantum realm. And I will mention the notion of state without values for some physical quantity, which is the key of the problem. And then I will discuss the structure of what is known as the space of states, which is of utmost importance in quantum physics. I will then highlight the key property of the quantum physical world, which is linearity. And then we go into the qubits, the simplest quantum system, and we'll show how to combine physical systems. And this brings a very essential and very unique feature of quantum physics, which is entanglement. And then we'll say a word about measurement, because it's also important for quantum computing. And then I finish with the general idea of quantum computing. But then, of course, you will have the whole week to dig into that more deeply. So, So I changed the slide, but it does not show on my screen. Did you see another slide?
Yes. Yes, it does.
Okay, so it changed online, but not in the room.
We are seeing the outline right now.
And okay. So now there are three different things. On the screen, online, and what I see on the computer, there are three different pages. Sorry. Let's see. I'm gonna.
Yes. Okay. It works. No.
Yeah, it changes online as well. Thank you.
Okay. All right. Okay, so now you see a slide with our ordinary classical world picture. Okay, good. So yes, so our representation of the world is very simple. It's familiar. It's simple because it's familiar. There are objective physical systems. They're made of matter, or whatever matter means, some substance. They're distributed in space, which is a 3D for all we know. It's evolving in time, and it does so according to some laws of nature, which have a quantitative aspect and which are deterministic. This is important. This is the classical view, and actually not so much changes in the quantum view. One important thing to note is that when we say it evolves in time, we mean that the system can be in different states, and the states change as a function of time. Now, this is a very important notion, the notion of state, and also the notion of physical system. So just to be sure, what we call physical system is an element of reality that can be designated, singled out, uniquely identified as such. So it's something that you can speak about, and which is well defined by itself intrinsically, whether you know it or not, but the system is what it is. And then there's the notion of state, which is what fully determines what the system is at a given time, and it characterizes the system exhaustively. If you know the state, you know everything you can know about the system, and everything you need to know to understand how it evolves. So that's important. And this, contrary to it is sometimes said, this is still exactly the same in quantum physics. So we can speak about systems, and they're always in a given state, which is what it is at any given time. And it also evolves as a function of time. And it also does that deterministically, even though, you know, there's the problem of measurement, which is a false problem, but which is there anyway, because as you know, well, we come back to that. But anyway, so this world picture actually is not changed in quantum physics, apart from the question of how we characterize the state of a system. And according to classical physics, each state is characterized by a set of numerical values for any relevant quantity. For instance, you have a system, it can have a certain temperature, certain energy, certain velocity. So you have a list of physical quantities which can have different values. And knowing the state of the system is exactly the same as knowing the values of any physical quantity relevant to the system. Now, in quantum physics, we discovered that there are states which don't have value for some physical quantity. And this is the key points. So these are the states without value, if you like. And it's nothing special about some states which don't have value. Any state doesn't have value for some physical quantity and does have value for some other physical quantity. So this is very important to understand. It's not like there are special states. All states are states in their own right. All states fully determine the system. It's just that they cannot be associated with a complete set of values for all quantities, but still they can be identified. Okay, so let's go into the Stern and Gerlach experiment, which is So there's still some delay between. So apparently you don't see the right picture now. This is very strange. I have a picture on my computer and it's not the same on the screen. Do you see online, do you see the slide on the Stern and Gala experiment?
No, we are at how to characterize physical states.
Oh my God. Oh, nice go.
Maybe you can
Let's keep him there. He comes and does magic.
Yeah, maybe you can just go back and
Okay, so I have to do twice or three times just until it works. Okay, let's move forward anyway. So Stern and Gala experiment is really well, according to me, the most important experiment and probably the best one to enter the quantum world. So it's actually the first qubit that have ever been manipulated. These are silver atoms coming out of an oven. And the idea of Stern, who designed the experiment and got the Nobel Prize, by the way, well deserved, is that, so there was the idea that the angular momentum of the atoms was, or the electrons in the atoms was quantized, but it was really the very beginning of these ideas. And the idea was to try to probe this quantization of angular momentum by making it visible macroscopically to actually see this quantization. And the idea is simple. You have an electronic angular momentum. To this is associated a magnetic momentum. And if you have magnetic momentum, if you are in a magnetic field, you will have a torque exerted by the magnetic field. And if the magnetic field is inhomogeneous, there will be a force also, which will cause the particle to move. Now, if the angular momentum is quantized, then the displacement will be quantized as well. So that's what they wanted to check. So I note here in the bottom that actually the thing that turned out to be quantized in that particular case was the spin of the electron, which was not known at that time and not until a few years maybe. But doesn't matter. The idea is the same, and the experiment worked. So not for the reason that they were looking for, but it doesn't matter. So the idea is you have here an oven. You just heat it. Some silver atoms go out of the oven, and they go through, okay, a collimator just to make sure it goes straight along the line. And then you go into a region between magnets so that the design such that the magnetic field is inhomogeneous. And therefore, according to the angular momentum, the particles will move up or down depending on actually the component of the magnetic momentum, like a little magnet, the component in the direction of the inhomogeneity of the magnetic field. So, and the deflection will be proportional to that component. So if, for instance, you have a magnetic field aligned here at 0 degree with the inhomogeneity of the magnetic field, with the direction of the inhomogeneity, then you will have the maximum deflection upward. If it's on the opposite direction, 180 degrees, then it will move maximally downward. And then if it's perpendicular, there will be no deflection, and at different angles, there would be different movement. So the expectation from classical physics would be that since the atoms going out of the oven have any orientation, their magnetic moment will point in any direction, and so the component, let's say the vertical component, will be anything, and so you will have a continuum of values, and therefore a continuum of deflections. Now, what is this is what you expect. So if you don't put any magnetic field, so you expect all the particles, this is the red line, all particles are collected on a screen exactly in the center because they are not deflected, right? But if you turn on the magnetic field, you expect the particles to be distributed over all possible places between the maximum deflection, when the magnetic moment, the magnet is aligned with the inhomogeneity, and to minus that maximum deflection. And simple calculations show that it should be flat. Now, when you do the experiment, what you find is exactly this. So some particles, some atoms of silver atoms are collected with maximum positive deflection, and some with negative maximum deflection. Exactly half with positive deflection, half with maximum negative, and nothing in between. As if all atoms were perfectly aligned in their magnetic moment with the magnetic field, or opposite to the magnetic field. When I say magnetic field, I should say magnetic field inhomogeneity, but it's roughly the same for these apparatus. But anyway, and well, this is actually the historic image where you see, so without magnetic field, everything comes in the center, and on top you see the displacement, but nothing in between. So this is quite impressive. Now let's look. Yes, okay. This is what I said. Yeah. This is strange, because how could the magnetic moment have only two orientation, exactly upwards or exactly downwards? We know that space is isotropic. Is that a problem? No, of course not, because you can then turn you can turn the apparatus, and you will see exactly the same in any direction. So the magnetic field breaks the isotropy, and the deflections are always along the magnetic field inhomogeneity, as is expected from classical physics. The difference is that it's either fully positive or fully negative, but nothing in between. So okay, again the slide that is shown is not the one I intend. Anyway, now it's better. Okay, so this is a front view, let's say, of the experiment. So you have the magnetic gradient, which is, let's say, here vertically, and what you see is that 50% of the atoms are moved, end up collected in the screen upwards, moving upward, and half downward. And this is random. This is quite strange. If you do one by one, you see randomly, sometimes up, sometimes down. Okay, now I said physics is isotropic, obviously. So if now you rotate the instrument and you orient in an inclined direction, as here, then you will still have 50% move maximally in the direction of the magnetic gradient, or maximally in the opposite direction, again randomly, half and half. So this is well, this is what is this is what it is. There's nothing more to be said about that. This is how nature works. Now we can try to put one Stern-Gerlach apparatus at the output of a previous one. So let's look on top. So we said after the Stern-Gerlach apparatus, you have half of the particles that have moved up and half moved down. If you take the ones which have moved down and you put another apparatus, you will see that now 100% of them move down. Somehow it's consistent. They say, I want to go down. If you ask again, what is the component of your magnetic moment? It gives the same answer. I said down, it's still down. And you can put 20 of those in a row, it's down, it's down. Same for in the bottom. If you collect the particles that have moved up, which means they had their magnetic moment, or it looks like they had their magnetic moment aligned with the magnetic gradient, and you do again, they confirm their answer in a way. So okay, yes. So okay, this is just another illustration. First, it's 50-50, but then if you take the ones which have moved up and you ask again, you can ask as many times you want, they will always say the same, and whatever the answer. Okay, so that's interesting. So it's random in the first time, and then it's certain. Certain means you want to, well, it's tempting to say the particles which have moved up do have a definite value for the magnetic moment, for the component of the magnetic moment along that direction, because if you ask anytime, it will say the same thing. So you can say this is the value, because in a way, having, oops, sorry, okay, I go back here. The instrument of Stern and Gala is a way to ask the question, what is the component of your magnetic moment in some direction? And by moving in some place, the particles answer. And so if it answers something once, it answers all the time. Now, let's do something more interesting. We do the same. We take the particles which answered up. And now, instead of asking them the same question, now we ask them the question, okay, now you told me that the component of your magnetic moment was along the vertical axis. What is the component along the horizontal axis? What will come out? So, of course, classically, you expect that if it's oriented vertically, the component along the horizontal direction is 0. Now, what you observe is that 50% will answer, yes, I am going to the right, and I'm oriented to the right, and 50% will answer, I'm oriented to the left. And this will be random again. So this is quite strange because it seems to be incompatible, but that's what happens. And now, if you, at the end of this, if you take the ones, let's say, which were moved to the left, saying that their component is maximally negative on the horizontal direction, and you ask them again the same question about the horizontal component, what will they answer? Well, they will answer for sure again the same answer, that is maximally negative along this axis. So it means that the particles here, and you can ask 10 times more, and they will say always the same. So once a particle has given an answer to a question, it keeps to it. But if you ask another question, you should be prepared having an answer which is not what you would expect classically. Okay, yes.
If for the second one you took only like a 45-degree angle, would you still get a 50-50 ratio?
No, and I come to this. That's important. So before we go there, so if I had taken, of course, the one which have answered, I'm oriented towards the right, and you ask again, it will say again the same. Okay, now, okay, before we do what you ask, let's do another trick. We take the one which answers to the second question. My component along the horizontal axis is maximally positive, let's say. So the ones which ended up here. Again, for those, you know they have a definite value of this component, because if you ask the question again, they will answer all the time the same. So you can say they have this value. They do have. Now, remember, these particles first came out of the first Stern and Gerlach apparatus, answering for sure here, when we took them here, they had a vertical component which was maximally positive. Now, we put them into this one, and we take the ones which do have a value for the horizontal component, and we ask them again the same question as the first one. Now we ask them, okay, you answered me, you have maximally positive here, and now what is your value? And the answer is 50-50, maximally positive, maximally negative. This is just the way it is. So all this sounds a bit strange. Obviously, having measured the horizontal component has put the system in a different state as what it was before, because now it does not answer the same. But interesting thing here is that when you take the particles which do have a definite value of the horizontal component of their magnetic moment, obviously they don't have a value for the vertical component, because if you ask, sometimes they will say plus, sometimes they will say minus. So that's interesting. Now, the notional question behind this is the notion of measurement. What is a measurement? You have a physical system, which is the measured system, and you have another physical system, which is the measuring system. The measured system has defined physical quantities associated with them, different type of things, temperature, velocity, magnetic moment, whatever. And the idea is you make these systems interact, and the evolution is, according to the laws of physics, the evolution leads to some manifestation which uniquely reflects a given value of the measured quantity. That's how you can tell the value that you have measured, right? So now I have another problem. Sorry again. I got it. Oh. Okay, we need someone. No. Yeah, please help. I don't know how to use this. I put 100%. Is it? Yeah, okay, thanks. Okay, so the Stern-Gala experiment is actually a measurement, in the sense that the behavior of the particle going through it depends on the value of a given quantity, and that quantity is the magnetic moment along a given axis, which is the axis of the magnetic field gradient. So, and the observational finding, and this would be the same for any measurement of any physical quantity. But in that you have some possible answers, and in that particular case, there are only two possible answers to any question of the type: what is the value of the magnetic component? The component of the magnetic moment along a given axis. And so it's either plus max or minus max. Let's call it plus 1/2 and minus 1/2. If we speak of the spin, should be minus h bar over 2, plus or minus h bar over 2. It doesn't matter. It's a given value, plus or minus. So there are only two possible answers. So whatever question you ask of the type, what is the value of the magnetic moment, it will answer one or the other. There are only two possible answers. But what we saw, what the experiment shows, is that there are states of the silver atoms which do not have any value of a given quantity like that. Otherwise, it would show it for sure. You know, because it's not like the apparatus is not a good measurement device. It's a good measurement device. Let's assume it's perfect. Of course, there are some construction imperfection, but in the principle, it's a perfect measurement. So when the system has a definite value, the system gives that value, and when but sometimes the system does not have a value. It's not that we don't know it, it's that it doesn't have one. So, okay, this probably I can skip. Yeah, so the particles which moved up in the first Stern-Gala device do have a well-defined value of the vertical component. But then and we know for sure, because if we ask again, it will give it all the time, 100% of the time, but it does not have a definite value of the horizontal component, because if you ask, it will say sometimes, so it has to answer something because you ask the question, you make it go through the Stern-Gerlach device, it has to end up somewhere, right? You have to collect it somewhere. If you put a screen, it will appear somewhere, it will just not disappear, you know? So it has to answer something, and there are only two possible answers. This is what the experiment shows. But since it does not have a value, it somehow chooses randomly one or the other. So this is what appears, at least. And then if it answers, let's say, -1/2 here, then it has this value in the sense that if you ask again, it will say again the same thing. So it's a value that you can attribute to the state. Okay, now your question. If you take an atom which goes on the up side of the first Stern-Gerlach. So we saw if you ask about the horizontal component, it will say 50-50 -1/2 +1/2. Note that the average is 0, right? Which is what you expect quite classically. Now, if you look for the component in a direction at 60 degrees, then what you find is you will find 3 times out of 4 +1/2, and so moved in the direction of the inhomogeneity of the gradient, and 1 time out of 4 in the opposite direction. Again, if you look at the average, 3/4 of 1/2 plus 1/4 of -1/2, you will find 1/2, which is exactly what you would have expected classically. But the classically expected answer, 1/2, is not available. Sorry, I should have said it's not 1/2. It would be 1/4, 1/2 of the 1/2. I'm sorry. So you expect 1/4 because you just have a cosine of 60 degrees, but this value does not exist. There's no possibility to have this value. So the particle answers randomly one of the two only possible answers, but the probabilities are well defined, and on average it gives the same. Okay, here for any angle it will be cosine square of θ/2 or psi square of θ/2. This would be the probabilities. Okay, so this is how it goes. Now, some general comment. Any state can be said to have a well-defined value of some physical quantity, well-defined. So whatever the orientation in that case of the magnetic moment, or of the spin, if you like, whatever the orientation, there is a physical quantity for which the state has a well-defined value. Which quantity? Well, the component along that direction. Then it's +1/2 all the time, or plus maximum, right? And so this is for any state. Like, it's not that there are some states which are strange. All states are the same. I mean, they're ontologically the same. There is a physical quantity for which they have a definite value, but there are also infinitely many physical quantities of the same type, like component of the moment in some other direction, for which the state cannot be associated with a definite value. It simply does not have a value for this physical quantity. So this is a bit unexpected, but after all, why should all systems have why should all states be associated with a definite value of any physical quantity? Of course, there is no reason for that, and the best proof that there is no reason for that is that it's not the case. So if you make some reasoning to show that it should be like this, it has to be wrong because it's just not the case. But yes, that being said, there is nothing random about any state. The fact that when you measure a given quantity of which the state does not have a definite value, the fact that when you do that, you have a random answer, does not mean that the state is random. The state is perfectly well defined. you can characterize it fully by saying, okay, which value it has for that specific physical quantity for which it does have a value. So there's nothing random about any state. That's very important to know. So the idea that we have physical system characterized with a well-defined state remains in quantum physics. Fortunately, there's nothing random in this. Yes, and then, okay, again, when you ask a question about a given value, about the value of a given quantity for which the system does not have a value, of course, it cannot answer in a definite way because it does not have. Okay, so, okay, let's move forward. So now the important thing is that when you analyze the results of the Stern-Gerlach experiment and many others in different conditions, you end up finding that the space of states of any given system always has a structure, and this structure is always of the same type. This structure is the structure of vector space. So I assume you all know what is a vector space. It's just a space which has the same properties as ordinary space vectors, like little arrows that we discover in elementary school. So what makes the structure of a vector space so special is that it's the simplest structure, simplest set of objects for which you can do two operations. An operation of addition, you can add two vectors, you can add two arrows, you put one at the end of the other, and then you link the starting point of the first one and the ending point of the second one. You know how to add vectors. So this is an operation with some properties. It's commutative and so on. And then you can also multiply by a number. If you have a given vector, you can have 3 times that vector or minus 1.5 times that vector. So these are two basic operations, and they should verify some properties between them, but this is the simplest, a very simple mathematical structure. And the thing is that with these two operations, you can do what is called linear combination. You have, for instance, number 1 times state 1 plus number 2 times state 2. That will give always another state. So this is the central, the main, maybe the only discovery of quantum physics, that the space of states is a vector space. So, which means you can associate with every state of a system a given vector. And if you have two states, you can combine them through a linear combination, multiplying by a number or adding, or you can do that as many times as you like. You will end up with another state, sorry. So you have a state of space which has this structure. There's nothing more to say about that. It's just a fact of nature. It's very important. Any state, so if you have two states, you can combine them linearly. This represents another state, and conversely, any state can be seen as a combination of a given state of states, which are a basis, let's say, of the vector space. Okay. Yeah.
Are we in a real or complex vector space?
So, are we in a real or complex vector space? This is very important, and it's a complex one, and I have a word to say about that. So, what did I say here? Sorry. Yeah, okay. So, let's say you have a physical quantity, Q. Oh. Yes. Okay. So, this quantity, in general, can have a number of possible values. So I call here Q1, Q2, Qn. So it could be a finite number of values, an infinite number of values. Most of the time, it will be something discrete. So it can be, like we saw before, -1 or +1, or 1, 2, 3, 7, and then stop. Or it could be, well, anything. But okay, you have some discrete set of discrete or not, but possibly discrete sets of values. Now, each of these values is associated with a state which does have this value for the physical quantity under consideration, Q. Now, because of the property we just saw, that the space of states is a vector space, you can form a linear combination of these states. So I call Qi with this little sign here, which you probably know, the state which has well-defined value Qi, and then I can form the state S here, which is just a linear combination where the alpha I are numbers, indeed complex numbers. I come to it in a second. So you do just this state multiplied by alpha 1, the state which has definite value Q2 multiplied by alpha 2, and so on. And this is a state because this is the structure of the state of space. Now, the relevance of this modeling is that I again made no, I made a mistake again. Sorry, I have trouble with. Oh, yeah, okay. Here it is. No, no. So this state, which is a combination of those states with definite value of Q, don't have a definite value of Q, but they have definite probabilities to manifest a given value of Q if you make the measurement. So this is what we saw with the Stern-Gerlach experiment. An atom which does not have a definite value of some component of the magnetic moment will have different, can be characterized not by the value because it does not have, but by the probabilities of finding any value if you make a measurement. And the modeling, in the modeling of this vector space, you can consistently associate with any state a combination of states which do have a definite value, such that the coefficients of the combination, the linear combination, give directly the probability of observing the given value if you make a measurement. And this correspondence is just that the probability is proportional to the module of the coefficient. Okay, let's take an illustrative example. I think it's important to realize that this is not something that is quantum associated with microscopic systems. This is a general property of any physical system. This is a property of the world, a property of the quantum physical world. If you have two states which are possible, then any combination of states are possible. Let's take the example of the physical quantity, which is temperature, and the system is the water in a glass of water, let's say. So on the left, you have illustrated a state of this water, which has a definite value of temperature, which is 300 K. Okay, and on the right is another state of the same system, glass of water, another state which has definite value of temperature, which is 400 K. So this state, which I know the one on the left, which I know 300 K like that, this state exists. Okay, very simple state. The other state, 400 K, also exists. Therefore, this is what quantum, not just quantum physics, this is the physics, this is the world. These two states exist. Therefore, the state 1/2 the first one plus 1/2 the second one also exists. I could put here any number. If these two states exist, and they do, then this is a state that exists. It's just a fact. Now it's important to realize that these states, 1/2 300 plus 1/2 400, is not a state which has 350 K as a definite temperature. No.
this state, 350K, exists also. It's also a possible state, but there's nothing to do with the state 1/2 300 plus 1/2 400. This is a combination of state. It's not a combination of the values of a given quantity, right? It's absolutely crucial. So now you would say, okay, you tell me this state exists, but then what is its temperature? Precisely, it does not have a temperature. But then you say, okay, but what happens if I put a thermometer in it? I can't put a thermometer in the glass. What happens? And then what happens is that you will observe 300K in 50% of the time and 400K in 50% of the time. This is what is called a measurement, okay? Note that this is what you will observe. I'm not saying that this is what exactly is the case. I come back to that later when we talk about entanglement. Anyway, likewise, the state square root of 3/2 300K plus 1 or minus 1/2 I imaginary number 400K also exists because it's another combination of two states that exist, and this is the basic structure of the state of space. If these two states here exist, this one must exist, and it does. And this state obviously is not a state with a complex value temperature, which would be square root of 3/2 300 plus I. Okay, so and of course there is no state with a complex value of the temperature. Okay, again, the mistake that should not be made is that this combination somehow combine the value of the physical quantity. No, they combine the states, and this is why this is why. So again, this state, if you measure its temperature, it will give you in 75% of the time 300K, and in 25% of the time 400K. This is just what occurs. So complex numbers. I put relax. We should not be puzzled about complex numbers. It's okay that the combinations are done with complex numbers, because and why should we be surprised by these complex numbers? Why should we expect that the numbers by which we combine the states should be real numbers? What's about the real numbers that we would expect that? Of course we don't. Again, if this state here had temperature 350, of course you could make only real number combinations, because the value of a physical quantity can only be real. Obviously, this is the real numbers are numbers by which you can define a quantity. Okay, but in the vector space of states, the numbers are not used to define quantities. They are used to combine states, and that's all. And now, if you don't forget this, that you are not combining value, but you are combining states, then it's clear that there's no reason why the numbers you use to combine states should be real. Indeed, they are not. And in fact, on the contrary, the complex numbers are much better behaved numbers to do a vector space. I mean, a vector space can be over any field of numbers, as the mathematicians say. Now, there are several fields of number. The rational numbers are a field of number. Then you have the real numbers, indeed, then you have complex numbers, then you have the quaternions, you have the octonions. The complex numbers are the most natural ones, actually. They are the most, they are complete. They are algebraic, the field of complex number is algebraically closed, which is not the case of the real numbers. Now, why not go to quaternions? But quaternions is not commutative anymore. And the octonions, they are not even associative. The most well-behaved field of numbers somehow is a complex number. Anyway, this is what we find in nature, and that's it. But again, relax, it's okay. Complex number, it would be a problem if they were measuring quantity. They are not, so it's fine. It's just combining, and that's just the structure of the world. Plus, this is very important because it's not well known. Actually, there's a mathematical theorem which I consider the most important in this field. It's the Gleason theorem, which says that there's actually no other way to model consistently. Oh, I missed the end of the sentence. To model consistently a situation where the manifestation of the physical system obey simple rules of probability. What time is it? I should accelerate anyway. Okay, so yeah, okay. And then the most fundamental property of the physical world is this one. Physics is linear. Physics is linear, which means that the evolution of any physical system under any circumstances respects linear combination. So this is crucial. First of all, if it did not respect linear combination, what would be the point of highlighting linear combination? I mean, when we say the structure of the vectors, or the structure of the state of space is a vector space, it means we can make linear combination of states, but of course, it has to reflect something in nature, because you can always define a set of objects and you define some linear combination and you say, okay, this is something. It has to be consistently, I mean, it has to reflect some property of the world. Otherwise, you can always combine what you want, but okay, you're just playing. So the fact that, I mean, what gives weight and interest in this modeling, because after all, it's a modeling, the state is what it is. We represent it as a vector. Why? Because there is a meaning in combining through linear combination with some numbers, and this meaning is how to say, confirmed or I don't have the English word. Okay. What proves that this has a meaning is that when the system evolves, the linear combinations are respected in the following sense, which is if you start with the system in state A, when you start with state A, the system evolves to state A prime. And then if starting from state B, the system would evolve in state B prime. Then, if you start with a linear combination of A and B with any number, alpha and beta, then the system evolves in a state which is exactly the same linear combination of the states that you would have obtained if you had started with only one of them. So this is linearity. Okay, this is a simple mathematical property, which is rooted. I mean, again, which gives its relevance to the notion of vector space. So that's why somehow it's because physics is linear that we can model by vector space in a relevant and consistent way. So this is absolutely, again, I mean, sorry. I think I got it this time. No? Yes, maybe.
I think it's okay.
I think it's okay. I should not
Just
move
right.
them. Yeah, sorry. Yeah, so this is really the crucial property. A combination of states evolves like the combination of the evolutions. Okay, this is absolutely crucial. Okay, now let's go to quantum binary digit, the qubits, which is simply the simplest possible physical system. Yes.
I mean, if we start with the state A and B, we have then the state alpha A plus beta B.
Yeah.
And then we hope this combination stay the same, or the alpha will change?
No, the combination remains the same indeed. So if A gives A prime, if B gives B prime, then alpha A plus beta B gives alpha A prime plus beta B prime with the same alpha, the same beta, the same combination. This is really a very deep, impressive property. This is how the world works, you know. And this is what makes the modeling of a state as an element of a vector space. This is what makes this pertinent. I don't know what to say in English, meaningful and useful. It's not like that we model the world like this. No, the world has this structure deeply rooted into its nature, its behavior. Yeah.
So that means that when if we measure for the A state, so we will get like alpha square probability. And if we imagine, because when we measure, the state will change.
Yeah.
If later we measure the A prime, we will get alpha square.
Yes. Well, so there is a subtlety, but yes, but there is a subtlety. If the state A and B are, let's say, orthogonal, if state A corresponds to a given value of some quantity and state B corresponds to another given value of that quantity, then if you measure that quantity in the initial state, you will have indeed module of alpha square probability of seeing A and module of seeing B. Now, if it's the same also in the final state, that A prime has a given finite value of a given quantity and B prime as another given value of the same quantity, then the probability of seeing one or the other would be module square of alpha and module square of beta. Now, it could be that A prime and B prime are not states which have a definite value of the same quantity. In that case, you will have what we call interference. And so the probabilities of finding a given value may not be module of alpha square and module of beta square.
In measurement, we cannot distinguish between A and A prime, right?
Between A and A prime?
Yeah, measurement. Because
yeah, yes, you can. It depends. If A has a given value of, I don't know, the velocity, and A prime has another value of the velocity, and you measure the velocity, then you will distinguish. Either you find A or you find A prime, you know, so it depends. This is completely general. So it can act on vectors or states which have definite values for some quantities. Remember, if you have definite value for some quantity, you don't have for some other quantity. So it always depends what you measure. But in any case, this linear evolution is always there. So I said in any circumstance, and of course, this is what pure quantum physics says. Now, some people would add, except in a measurement situation. But this is a bit subtle, and maybe we'll come back to that later. So a qubit is just a system which is simple as possible, for which you can easily distinguish and identify two states. So you can call them plus 1/2, minus 1/2, as we did before for the spin of an electron, say. It could be black and white, heads and tails, whatever. Usually in quantum computing, we call that 1 and 0. You can call that plus or minus, whatever. You distinguish two states. It's just like when you toss a coin, it's heads or tail. Of course, there are several ways to be tail. You can rotate. There are several ways to be heads, but you can identify a set of states which you call heads, and set of states you call tail. A qubit is something for which you can distinguish and identify two states. And then, of course, let's call them heads and tails. So if the state heads exist and if the state tails exist, then any combination exists. That's the basic rule. Okay, you can always do any combination, and it remains a state of the system. So you cannot have a system which only has two states. If it has two states, then it has an infinity of states, which are all the combinations with any pair of quantum number. So again, beware, alpha heads plus beta tails is by no means a stranger state than heads or tail. It's not because it looks like a combination of both that it's something stranger. Remember that this state here for the orientation of the magnetic moment is no more stranger than this one or this one or this one. Of course, you can express one as a combination of the others, but you can express the other as the combination of two others as well. Any direction in a vector space it's not the same direction, but it's has the same value. There's no specific direction. Yes.
Just briefly before, for a qubit, do you want these two identical states to be orthogonal to each other?
Yes. When I say can easily distinguish and identify two states, so that's what I mean. So, by the way, that's an important point. If two states have definite value for a given quantity, and this value, so remember, most of states don't have a value for any arbitrary quantity. But if two states have a definite value for a given quantity, and these values are different, then they are orthogonal. Okay? That's the way we actually, that's our choice. We decide which scalar product or Hermitian product we put on the vector space. But we design so we decide that if you have well-defined value and different value, then you are orthogonal. I mean, this is a reasonable thing to do. It's our choice, but this is the choice that allows the rules that we mentioned. Okay, so relax again. There are no superposed states, or all states are superposed. You always hear superposition principle. This system is in a superposed state. It means nothing. I mean, again, every vector can be decomposed into a linear combination of other vectors. It's the same for all. Now, it's better to speak of combined state because it's not a I don't know what superposition means. You put one on top of the other. What is that? But you combining, I know what it is. It's linear combination. This is the definition. This is really the status of a vector space. So again, this arrow is not a superposed vector. What do you mean? It's superposed to what? Okay, and you would not say it's both vertical and horizontal just because you can have it by summing an horizontal or vertical. You can say that if you want, but don't forget that this state alpha heads plus beta tails has nothing special compared to heads or tails. It has something special if you want to measure the head-tailness of the state, because then head is a state which has a specific value for this head-tailness, and the tail as well, and the other one does not. Okay, but it has definite value for some other quantity and so on. So anyway, so yeah, don't say a qubit in state alpha 1 plus beta 0 is in a superposed state, while a qubit in state 1 is not. Sometimes you hear, oh, one is a pure state, but the other one also is a pure state. They're all states, okay? Well-defined, no problem, okay? So say rather that this does not have a definite value for the specific physical quantity with measurement unambiguously distinguish 1 and 0. But so what? It doesn't make any fundamental difference from the physical point of view, and it does have well-defined values for other quantities. Okay. Likewise, don't say an electron is both here and there. This is what we hear all the time. An electron can be in two places at the same time. It means nothing. It cannot be at two places at the same time. But you can have no place. It's just that the quantity position, which you can take coordinates in Cartesian coordinates, there's no value for the state of the system. There's no value of the x component. That's it. Fine. But it does have a value for something else. Okay? So it's not, yeah, anyway. Okay. So by the way, this is the type of combination that we saw for the silver atoms of the Stern-Gerlach experiment. So the horizontal orientation is actually half vertical plus half vertical up plus half vertical down. So you would say, oh, this is a combined state. Yes, it is a combination of those. But don't say this is a pure state while this is a combined state, because this pure state is actually also a combination of this one and this one. Then this one are pure after all, and this one is combined. You see, it makes no sense. It's a vector space. It's just what it is. So you can express any vector in terms of combinations of a basis of vector. So a qubit is a system for which you can have a basis with only two vectors. So all the infinity of the states can be obtained as a combination. Okay, now very important, and I think I should go faster and maybe stop you. You stop me when you want. So okay, again, it did not change. Still not. Sorry, the slides are not going through again. Okay, now it's done. Okay, entanglement. This is evidently very important. So now let's go to a system of two qubits, and it would work for any composed system, that is a system that you can consider as the combination of different subsystems. So let's say now we don't have only one qubit, we have two qubits, let's say qubit A and qubit B. Now you can ask yourself, okay, I know the space of states for this new system. It's a new system, you have two qubits, it's a system of two qubits, okay. What are the possible states of this system of two qubits? What you know is that if you identify two of these states, any combination, linear combination of these two states will be another state. So you know it will be vast. Among the possible states of this system of two qubits, you can have obviously the following ones. You can have a state in which A is in state 1 and B is in state 1 as well. It's obviously a possible state. This is noted like this. 1 and this cross, this is a tensor product, which turns out to be mathematically the only way you can combine meaningfully the two vector spaces. This can be easily demonstrated, I mean, in a way that respects linearity. But anyways, let's take it now as a notation. So if A is in state 1 and B in state 1, you note this is obviously a state which exists, and you note it 1 cos 1. Okay. Now, of course, another possible state is that qubit A is in state 1 and qubit B in state 0. Then this is another state. Obviously, it's not the same, and it's noted like that, which, okay, it's a notation which makes sense. And then you have also another combination with A is in state 0, B in state 1, and A in state 0, and B in state 0. So you have here 4 states, and obviously, because you have these 4 states, you can have any combination of those, right? But before we go there, let's see this other obvious state of the system. Qubit A could be in state 1, and qubit B could be in another state, which is perfectly possible for qubit B, which is alpha 1 plus beta 0. B could be in 1 or 0, or any combination of those. In particular, it could be in this alpha 1 plus beta 0 state. So if you have qubit A in state 1 and qubit B in state alpha 1 plus beta 0, then this gives this state 1 cross alpha 1 plus beta 0. And this can be rewritten as a combination, linear combination of 1, 1 and 1, 0. You see, by applying some sort of distributivity. This is how it works. This is not a trick. This is, again, the only way to combine vector spaces in a mathematically meaningful way that is respecting linearity. So this is just it. And more generally, you can say, okay, the most general state in which qubit A can be found is something like that for some alpha and beta. And the most general state in which qubit B can be found is something like that with any gamma and delta. So now a state in which A is in this state and B is in this state would be this state. So you just do the cross, the tensor product between these two states, and you have this particular linear combination of these vectors, these states, right? Okay, so, oops. Yes. Okay, now the point is that not all states of the system, of this system of 2 qubits, are of this form. These are obviously existing states. Therefore, any combination is of this, is again a state. Now, any combination of that gives many, many, many more states than states of this type. Let's show this briefly. Again, the most general state of A is some alpha 1 plus beta 0. And the most general state of B is some gamma 1 plus delta 0. Therefore, you can have a state of the system which is a given state for A and a given state for B. And that will give something like that. This is the most general form. But there are other states, because these 4 states are existing states. Therefore, all combination of these 4 states, A11 plus B10 plus C01 plus D00, for any A, B, C, and D are possible states. Now, in general, such a state is not of the form state of A cross state of B. This is very important, and this is easy to see because if it were a state of this form, you would have coefficients here, alpha gamma, alpha delta, beta gamma, beta delta, and you can see that if you do alpha gamma times beta delta, it's the same as alpha delta times beta gamma. So a state of the system which is a given state for A and a given state for B is a combination of 1, 1, 1, 0, 0, 1, 0, 0, for which A times D equals B times C. And this is obviously not always the case. You can do an infinite number of combinations of these 4 basis vectors for which AD does not equal BC. So it means that for all these states of the system for which AD does not equal BC, there is no way you can express this state as a combination of a given state for A and a given state for B. It's just a fact that most of the states of the composed system, composed of 2 qubits, most of the states of the composed system is the state in which there is no state for each individual system. Just as before, you can have a state with a given value of a quantity, but some states don't have a given value of the quantity, like half 300K plus half 400K. It does not have a value of temperature. That's it. In the same way, there are systems of there are states of a system of 2 qubits which do not have a state for each individual system, a qubit. This is just a fact. It's unavoidable because of the vector space structure. Okay, again, relax. Okay, the most general state of a combined system is not a state in which each component, each subsystem has a state, but the global system is in a perfectly well-defined and unambiguous state. So it's not like there's something strange or random about the system. The system is in a perfectly well-defined state. We know, or we don't know, but we can in principle know the state of the system. And in this state, we know that there is no state which can be attributed to any of the subsystems. Okay, so what? It does not prevent us to perfectly characterize the system. We know its state, therefore we know how it will evolve. I mean, we know the environment and if we know how to calculate, but I mean, there's no problem of principle. The state, the system is in a perfectly well-defined state, not ambiguous, and the evolution of that state, so of the global system, is perfectly well-defined and will obey the laws of physics that are known or not known, but there's no difficulty in that. And how does this system evolve? Well, still according to linearity. If you know the evolution of 1, 1, the evolution of 1b, 1, 0, the evolution of 0, 1, the evolution of 0, 0, then you know the evolution of their combination. They will evolve as the linear combination of, they will respect the linear combination. Okay, I could say a bit more, but I think I should get to the end. It's okay, we can, okay, I go quick. So, quantum computing, it's about time, right? So again, linearity is the key. So how does it work? It's extremely simple in principle, then we have to do it. But the idea is that you start with n qubits. And obviously, these n qubits, so qubits, let's say, of the same type, it doesn't have to be, but let's say, take qubits of the same type, which can be in state 1 or 0. So you identify some physical quantity which you can, let's say, easily measure, and for which there are two possible values. Let's call them 1 and 0, it doesn't matter, or heads and tail, what you want. So you call them 1 and 0. So each qubit can be in state 1, could be in state 0, but could be in any combination of these. Fine, it's just another state. Now, there are states for the global system. There is a state which is each of the qubit is in state 1. So it's 1, tensor product 1, 1, 1, 1. Okay. Then there is another state where the first is in state 0 and all the other one in state 1 and so on. And so you have all the possibilities. All these are states. And actually, they constitute the basis of the state of space of the global system, which is just the union of the n qubits. So of course there are 2 to the n possibilities like this. So the vector space of the global system of n qubits has 2 to the power n dimensions. Okay, that's just the way it is. Now, so the idea, again, then you have to see how to do it. But this part is not the most difficult part anyway. So you start with n qubits, and you start with some state, which is a combination of the basis vector state. That is just some state of this system. And then you make it evolve in a clever way. So how did it work? So you have an evolution, so the system is subject to some environment, and so it evolves. Okay, so let's say that if you start with state 1, 1, 1, 1, 1, it evolves into what I call evolution of 1, 1, 1, 1, 1. I could call it 1, 1, 1, 1, 1 prime. Anyway, so just if the system were in state 1, 1, 1, 1, 1, it would give evolution of 1, 1, 1, 1, 1. If it were in 0, 1, 1, 1, 1, 1, it would give evolution of 0, 1, 1, 1, etc. And then because physics is linear, if you start with this combination, you will end up with this combination, which is the same combination of the evolved state. Now, if you're clever, if the algorithm is well designed and well implemented, so it does exactly what it's supposed to do, then the resulting state will, so you will design the evolution, so the algorithm and its implementation, so that starting with a given state that you can produce, that you can fabricate, you will end up with the resulting state, which is just this, such that all the coefficients in this combination are 0. Okay, there's an ambiguity here. I missed a line. I'm sorry. I missed a line. No. Okay, I cannot correct. Can I?
Yeah, I think you can write it.
You think I can write here?
No, even here.
No, here. Sorry, I made a shortcut, which is you think? But it will not be seen online anyway.
Yes.
Okay, so let me explain what, there's just one line is missing, but it's obviously crucial. Because as I said, the evolution respects linear combination, right? And this actually comes to the question that you asked before. So this is the end product, obviously. Now, evolution of 1, 1, 1, 1, 1 itself is some state. This state is some combination of the vector state, okay? So it will be, let's say, yeah, so I don't know if you can see online my mouth. Yeah, but people won't see online.
Okay.
Yeah, they will. Okay. So thank you very much. So, okay. So we have 1, 1, 1, 1, 1 evolution of 1, 1, 1, 1, 1 plus a 0, 1, 1, 1, 1 evolution of 0, 1, 1, 1, 1, etc. Okay, plus a 0, 0, 0 evolution of 0, 0, 0. Okay, so this is the output. Okay, let's see here. Can you see online or? Yeah, okay. So this is the outcome of the algorithm. Now, each of these is a combination on its own of 1, 1, 1, 1, 1. So it's let's say I call it it's okay, alpha plus beta 0, 1, 1, 1, 1 plus I don't know zeta 0, 0, 0. Okay, it's some combination. This one is some combination of the vectors. This one also is some combination of the vectors, but another one with some alpha prime, beta prime, etc. And so each of these is a combination of the basis vectors. Okay, and when you do this sum, you end up with another combination. Let's say this time B 1, 1, 1, 1, 1 of 1, 1, 1, 1, 1 plus B 0, 1, 1, 1, 1, 1 0, 1, 1, 1, 1, 1 plus etc. plus B 0, 0, 0, 0, 0, 0. So you have 2 to the power n basis vectors. So you start with A1 with a certain combination of this basis vector. Each of them, you evolve that state globally, which gives you the same combination of the evolutions, and this thing is some of the combination. And the idea is to design the evolution, the algorithm, so that this final combination of the basis vector is such that all B, A, J, K, Z equals 0 except one of them, except, let's say, B1, 0, 0, 1, 0, 1, 1, 0, 1. Okay? And then you make a measurement of the physical quantity for which for which state 1 has value 1 and state 0 has value 0. You make a measurement on the global system, and because they're all 0 and there's only 1, you will find this. You will find the state, you will find the state corresponding to this B, because it's the only one. So it has a definite value. The combinations don't have a definite value if here there are several numbers which do not, which are not 0. If you make a measurement, you will have randomly one or the other, and so what's the use? Because people always are confused. How can, I mean, qubits are such that, so you have a combination. Okay. Anyway, yeah, you have a combination alpha 1 plus beta 0. So, because you know, we always say, okay, quantum qubits are so much more powerful than classical bits, because in addition to being in state 1 or 0, you can be in an infinity number of states, alpha 1 plus beta 0. So, oh yes, many more states with just one qubit. But then, okay, if I measure this, I don't know what I find. Sometimes I find 1, sometimes I find 0. How can this be helpful? I cannot know the state of the system, because if I measure, let's say I measure this state, I find 1. Does that mean that the state was in the system was in state 1? No, it could have been in any state with just non-zero alpha. So how can this help? The point is, it helps because if you design properly the evolution, so the algorithm, you can make the system end up in a state which is a pure state from the point of view of the quantity that you will measure, so that they're all 0 except 1, and then you are sure of what you are going to find. But you see that, so it's powerful because you can use, you can perform the evolution on one system in one state, but the resulting state of that system is a combination of the resulting evolution on 2 to the power n different states. Again, this is of no use if then you make a measurement and you have probability to find this or this or this. What do you learn? But if you design properly so that these different evolutions interfere in such a way that in the end there's only one state coming out, and this state is the state which is the result of your problems, then you're done. And this can be extremely powerful. This is how it works. So you get rid of the randomness. I mean, randomness is not something that is built in quantum physics. Randomness is just because if you measure a quantity for which the system does not have a value, of course, you will have a random answer. But if it does have a value, it will tell you the value if the measurement system is well done. So the idea is to make the system evolve into a state which has a value for what you measure, and that this value is the answer to your measurement. So then it's exactly like a classical computer at the end. It's in a state which is well defined and has a given value of some quantity that you measure. Then it will give you this value. The thing is that if you use qubits, then you can perform, you can cleverly design the evolution of the system so that starting from a state which is, this combination, it will give you the answer with a considerable gain of time. So that's the idea. Now, I don't know if, oops, no, wrong way. Yes, I don't know if I can, maybe I should stop. Oh, yes, my God. I wanted to discuss measurement and entanglement, but maybe I should not. You think I can? Okay, I apologize for the people online if it's a bit long. So there's something important because this is the reason why it's not so easy to do quantum computing, even though it can be powerful as we just showed. So, and it's a fundamental question for, let's say, philosophy of quantum physics. So it's a question of measurement and entanglement. Remember the Stern-Gerlach experiment. You have an oven and there are particles, silver atoms going out. They have a magnetic moment oriented in some direction. The direction does not have to be the direction of the magnetic gradient in the apparatus. But the apparatus measures the component along a given direction, that of the magnetic gradient. So essentially, the Stern-Gerlach device measures the magnetic component in a given direction. So first, the particles go out of the oven in any direction, so not surprising. There are only two answers possible, plus or minus. 50% are plus, 50% are minus. Now, if you take the ones which go out at the upper place of the device, now they are in a well-defined state, which is this one. And as we saw, when you are in this very well-defined state, and you measure now the horizontal component, putting another Stern-Gerlach apparatus behind, you will find randomly 50% on the left, 50% on the right. Now, I say this cannot be true. This is what we observe, though, but this cannot be true. And it is not true. It's true that this is what we observe, but you can see that this violates linearity, which we discussed before, and it also violates determinism, which is a problem, even though some people insist in saying that nature is not deterministic. Nature, I don't know, but quantum physics is deterministic. It's just a fact. It's linear, deterministic. The systems evolve according to an operator, which is a unitary. But anyway, I don't want to go too far into philosophy of quantum physics. But anyway, recall this. The state with orientation up is half the state right plus half the state left. In this half plus, this is linear combination. It could be quantum numbers, it could be, sorry, complex numbers. It turns out it is this combination. Fine. So this is the case. This is, okay. This state is a combination of these two. It's a perfect qubit, by the way, from the point of view of the spin. So there are with two orientations, you do all the states. So this state is the combination of this one. Now, let's say that we measure on this state, let's say that we measure the horizontal component of the magnetic moment. So we orientate the Stern-Gerlach apparatus horizontally. We all agree that if the state of the atom was like this, so oriented towards the right, then the outcome would be that all the time, 100%, because this atom has a definite value of the horizontal component, which is plus, let's say. So it will move, it will move according to plus. If the state of the atom is this one, oriented in the left direction, then the outcome will be that it will be deflected on the left. This is just because it's measuring this component for which the atom has a definite value. So this is true 100% of the time, 100% of the time. Now, what does linearity tell us? It tells us that if these give this and these give that, then half of this plus half of that gives half of this plus half of that. It's just a fact. That's linearity. This is the deepest thing, and there's no way. I mean, this is also, of course, how quantum computer works, but this is how nature works. If you have a combination of states and you make it evolves like the combination of what you would have obtained if you evolve just the single state. So this is the outcome. And now, and this, by the way, is an entangled state. In this state, half this plus half that, there is no state for the atom. In particular, where is the atom? Well, in this state, this one, the atom is on the left. In this state, the atom is on the right. It has a position. In this state, it does not. And that's fine. It's not like it's a mystery state. This state is perfectly well defined. It's the combination of this one and this one. And you say, okay, but how does it behave? Easily. If you know how this behaves, and if you know how this behaves, then this combination behaves as the combination of what the individual part behaves. So there's no mystery in this. This is a perfectly well-defined state. The only thing is that it does not have a defined position for the atom. Okay, so what? So, but then you say, okay, oops, yeah. Okay, then you say, why don't we see that? Because if you do the experiment and you put a screen and you look where is the atom, you will see it up or down. Oh, yes. So the answer, why don't we see that, is because so far we are not there. If you want to explain what you see, then okay, you are part of the system now. You see something, so there is you. First, you put a screen, so you should put the screen. So okay. So we are not there now. We are here. We are just talking of the state of the system at the output of the Stern-Gerlach device. Again, this is what quantum physics predicts, and this is what is. Now you say we don't see that. Okay, but sure, we are not there. So let's get it there. So now, if the state was that, the outcome, including us now, including me, I, would be, it goes on the right because it was plus on the right, and I see it. So this is the new state of the system. I see that it is on the right. Ah, okay. This is the state of the global system, me, the atom, and the screen and the Stern-Gerlach apparatus, me and the universe. Okay. If the state of the atom was pointing to the left, then the outcome is perfectly clear. Since the apparatus measures the component and it has a definite value of the component, it will reveal this definite value of component. So the atom will occur displaced on the left. And if I look at the screen, I will see that because this is where it is. It's a well-defined position. There's no ambiguity. So if the state was that, here would be the icon. If the state were that, here would be the icon. Therefore, if the state is half of this plus half of that, the outcome is half of this plus half of that. This is linearity. In any circumstance, there is linearity. So now the state of the system is half I see the atom displaced on the right, plus half I see the atom displaced on the left. Now, what is this? Well, it is what it is. But of course, the thing is that now we are entangled with the rest of the system. As I said, in this state, this is perfectly well-defined state, but it's an entangled state in the sense that there is no definite state for the subsystem atom, and there is no definite state for the subsystem Stern-Gerlach apparatus. Now the same occurs here, now that we are in the game. There is no well-defined state for the system myself, and there is no defined state for the system particle. But there is a perfectly well-defined state for the global system, and this is the state. Now, how to interpret this state, which is a combination of two states in which I see something and I see some other thing. So, as I say here, now could start a very, very long discussion about what it means. But because now we are entangled with the system. But anyway, when we do the experiment, quantum physics says this is the output, and what we observe is 50% time this, 50% time that. Okay, let's admit it. So usually what we do is we make a simplification. We say, okay, if I see that, then it means that, well, it's not strange that I can see that, because this state here, the state I see this, is present in the system. And so the perception of this is there, and indeed it occurs, but also the perception of this is there, and it also occurs. This is what quantum physics says. But if this perception occurs, then, I mean, whoever you are perceiving this is the component of the system in which you are, and then the system goes on like that. So what you do usually, you simplify and say, okay, if I perceive this, then let's forget about all the others, and let's continue with this. So this is what is called the Copenhagen, what I call Copenhagen simplification. It's called Copenhagen interpretation. But anyway, let's not go into that. Why did I want to mention that? It's because now, because of the question of decoherence, and that's my last slide, or maybe just last but one. So now, the thing is that any physical system will interact with many other systems in the environment in a huge number of ways, right? So if you have a system, so, okay, and the evolution always respects linearity. So if you start with a system in state one, then after some time, it will evolve into, if you start with a system in some state, which is a combination of states. Any state is a combination of states, but a combination of states that you can measure, right? Easily with you can be aware of the result of a measurement of a given quantity. So a state which is a combination of states with well-defined values of some quantities, different ones, but it's a combination of different values a combination of states having defined values of quantities, and you make it evolve. Then, if the state started from a given value, it will evolve in a state one for the system, plus a state one of the environment, plus a state one of the measuring device, plus a state one of the observer. So that would, now, if you started with a different value, it would give you the same well, it would give you, sorry, a different combination of states of the system, the environment, the measurement, and yourself which looks at it, and so on. So, and now if you start with a system in a state which is a combination of all these, it will evolve into a combination of all these as well. And this is decoherence in the sense that you will end up with a state of the global system, which includes the entire universe, or maybe all the region which is closer to the speed of light the time you do the experiment. So, okay, and everything will be entangled because of linearity of evolution. And so very quickly, you end up with a state which is in this sort of configuration, so a combination of different evolutions and different interactions with the environment. And very quickly, you do not manipulate anymore the state of the system. You manipulate the state of the system and the environment and the device and yourself and your friends and so on. So, and then you cannot control. So this is, and this is definitely, and it's an entangled state. So there is no state anymore of the system. But for your algorithm, you want to have the system in a state and you make it evolve such that in the end, you make a measurement and you have your answer. But at some, very quickly, if the state is in some environment, it entangles with the environment, and then you are not manipulating the system, you are manipulating everything. You know, so you cannot make the system evolve independently of the environment just because it does interact with the environment. And as soon as it interacts, just as we saw before, as soon as you interact with the Sterniger, you start to entangle. It's always the same. So this is really my last time. The challenge of quantum computing, you don't see it again? Yes. The challenge of quantum computing is that you want to act on the system of qubits so that it evolves according to the desired algorithm, but you want to not act on the system of qubit so that it does not get entangled with the environment. So you want to act on it, but it should not. And how do you act? You build an environment which makes it evolve according to your algorithm. Otherwise, it does nothing. So you want to act on it, but you don't want to act on it because if you act on it, then it starts to be entangled. So it's not easy. Can it be done? So I would say, sure or no way. This is up to you. I don't know what's the combination here. No, actually, I think it can be done. Actually, it can be done for sure because it has been done. But to what scale? The more qubits you put, the more it's hard to isolate from the environment so that you act on it in the way you want, but you don't let its state mix or entangle, that's the technical term, with the environment, so that in the end you don't manipulate the system. You are yourself. I mean, the machine and the environment are all entangled, and then you don't control the algorithm anymore. So that's really the point. That's why I wanted to discuss this problem of measurement and entanglement, because that's just the way it is. When you measure something, it appears random because, okay, it appears random. This is a long discussion. But what happens, because of linearity, again, it's just linearity, what happens is that you entangle. If the state was this, it would give this. If the state was that, it would give that. If the state is alpha this plus beta that, it will give alpha this plus beta that. That's just the way it is. And there's no way out. And this is the good thing. That's the way we can manipulate qubits in a way that makes the quantum algorithm so efficient. But then the consequence of that is that you have a difficulty. Oops. Yes. You have this challenge, which is the fundamental challenge of quantum computing. So let's solve that. It can be solved. Okay, I should stop. Thank you.
Thank you.
And sorry for being so long.
It's fine.
Okay.
It's because of that. Is there some very quick question for Professor on Zoom or on site?
I lost everyone at the end. I was too long, I'm sorry.
No, we
No?
understand all
Okay.
you say. Yeah,
Okay.
yeah.
Good.
Perfect. So thank you.
Okay.
We wrap up for. Thank you, Professor. So let's proceed. We have a certain delay, so we will move on directly for the hand-on practice for getting started. I would like to introduce Jiron from KAIST, Korea. Please, can you share the screen?
Yes. I'll
Please.
just- Can you see my screen?
Yes.
I think okay. But before I begin, thank you for the great presentation from Professor Parizot. I think it was great introduction for us to start with the quantum computing. And before I start, I'd like to just give you a quick note for the Q&A. Please post your questions in the Discord channel. We have Getting Started with Qiskit channel on the Discord, and I'll make sure to answer that right away after the presentation. Okay, so let's begin. Good afternoon, everyone. I think it's afternoon in Paris, and welcome to Getting Started with Qiskit. Today's session is all about getting your hands dirty with some quantum circuits. This means not just learning the syntax, but understanding how quantum computation actually works. So by the end, you feel kind of comfortable building and running real quantum programs. So let me quickly introduce myself. I'm Ziyoung Jang, but everyone calls me Jim, and I'm a PhD candidate at KAIST, focusing on experimental quantum simulation and some hardware techniques like optical tweezers. And also at the same time, I'm working on theoretical aspects with Bin's team. And as a Qiskit advocate and a co-organizer for this event, my goal is to help bridge the gap between the theory of quantum computing and its practical applications. And if you want to connect, there's a QR code here for my LinkedIn profile. So please feel free to connect, or you can find me through GitHub. All right, now let's talk about what we're doing today. So here's the plan. You'll learn the basics, build circuits, and run them using fake freeze-brain. This part is crucial because it simulates real hardware noise, which teaches you how quantum computers actually behave versus like how we wish they behaved. And you also learn about the sampler and the estimator, which represents two fundamentally different ways of extracting some information from quantum systems. And the format is simple. I think the number is kind of missing in the presentation. You'll hear about 10 minutes from me, and then you'll work through the hands-on lab at your own pace. And if you get stuck, we have a Discord channel, as I mentioned earlier, and please feel free to ask and discuss. And okay. So before we dive in, let me give you some context about Qiskit itself. So what is Qiskit? Qiskit is a Python SDK for quantum computing. It's open source, developed by IBM, and it has become the standard tool because it bridges the gap between abstract quantum algorithms and actual hardware constraints. What makes it Qiskit so powerful is that is Python first. So you can leverage everything you already know about programming. But it also handles all the quantum specific things like unitary operations or measurement collapse and like hardware topology. Plus, it has great visualization tools that help you see like what's actually happening to the quantum states. And by the end of this session, you'll be building circuits just like this one you see here. Okay, so now let me show you how the lab is structured. The lab has the 19 exercises in total, organized into 4 sections, and they're designed to build your understanding progressively. So the first section here, we have exercises 1 through 5, which covers the fundamentals. And this is where you'll understand how quantum gates manipulate probability amplitudes and phases. And the next section we have exercises 6 through 9 covers advanced techniques, where you'll see how quantum circuits can make decisions based on some measurement outcomes. And the exercises 10 to 13 introduces the sampler and estimator, which are used to extract different types of quantum information. And finally, exercise 14 through 19 tackles the real-world topics like how to mitigate errors when your hardware isn't perfect. And there's also a solution notebook available. You can find it on the GitHub that we provided, but please try it on your first, because making mistakes and debugging is like how you build a real intuition for quantum behavior. Now, let me highlight a few key concepts, starting with quantum gates. So quantum gates are like the heart of everything you'll do today. But unlike classical gates, these gates manipulate complex probability amplitudes, not just simple bits. So for the X gate here, example, it flips the amplitudes between 0 and 1 states. And the Hadamard gate creates superposition. It puts a qubit into a state where measurement outcomes are fundamentally probabilistic. And the S and T gates rotate the phases, and which affects interference patterns. And lastly, the CNOT gate here creates entanglement, which is a powerful correlation that has no classical equivalent. And the code here shows the syntax, and you create a circuit and apply a Hadamard gate to create superposition, and then use a CNOT to entangle. This simple sequence is the foundation of most quantum algorithms. So speaking of superposition and entanglement, let's look at those more closely. So superposition means a qubit exists in a coherent combination of multiple states simultaneously. This doesn't mean it's randomly in one or the other, but that it's genuinely in both until a measurement forces a choice. And entanglement is when qubits become correlated in ways that violate classical intuition. The Bell state shown here is a perfect example of correlation. This means measuring one qubit instantly determines the other, regardless of a distance. So basically, if you get the outcome of 0 state for the second qubit, which the one that I'm pointing at, you always get the first 0 qubit as the first qubit correspondingly. And a quick note here, I like to mention that Qiskit uses the little endian ordering. So the first qubit is the rightmost qubit. This is important to remember because when you're reading measurement outcomes, you'll need to consider it. And now, once you build your circuits, you need to run them and extract information. And that's where the premix comes in. The sampler and estimator represent two fundamentally different questions you can ask a quantum computer. The sampler here asks the question like, what are the possible measurement outcomes? It gives you bit strings and their probability distributions. This is perfect for algorithms where answer is encoded in the measurement results, like with Grover's research. The estimator, on the other hand, asks like, what's the expectation value of an observable? It gives you a number that represents properties of the quantum state. This is quite essential for variational algorithms where you're trying to minimize energy and or optimize parameters. Understanding which primitive to use depends entirely on what information your algorithm needs to extract. But before you can run any circuits, you need to understand transpilation. Transpilation is where the theoretical meets the practical. Your high-level circuit needs to be translated into operations that the actual hardware can perform. Real quantum computers have constraints such as like limited gate sets, specific qubit connectivity, and some noise characteristics. Transpilation maps your logical qubits to physical ones. It decomposes gates into native operations, and it optimizes everything to reduce circuit depth, which directly reduces errors. And there are optimization levels from 0 to 3. Higher levels produce shorter circuits, which means there are fewer opportunities for decoherence and gate errors to accumulate. So this is kind of critical because current quantum computers are in the noisy intermediate scale era. And now that brings us to the backends we'll be using today. So we are using fake Brisbane instead of real hardware. And this is actually a kind of bad pedagogical advantage. Fake backends simulate real-lasting noise, things like gate errors, decoherence, and readout errors. This helps you learn to think about quantum computing in realistic terms, not just in ideal textbook scenarios. This diagram here shows the real fake Brisbane topology, and you can see how the qubits are connected. So not all qubit pairs can interact directly, and this connectivity constraint is a fundamental hardware limitation that affects how you design your algorithms. And understanding these constraints now means the skill you learn will transfer directly to real quantum hardware. So you're not just learning to code, you're learning to think like a quantum algorithm designer. Now, let me point you the resources you'll need. So as I've mentioned, the Discord channel is under the hands-on practice category. Please take a look. And that's your go-to for real-time help. And please don't hesitate to ask any conceptual questions, not just for debugging help. And all the materials are in our GitHub repository under day 1, and then the beginner notebook folder. And remember that learning quantum computing is iterative. So you'll understand these concepts more deeply each time you work through the problems, right? All right, then that's enough from me. So I'd like to get you started. So please navigate to the Qiskit Fundamentals Lab Jupyter Notebook. And you'll see this setup cell at the top. You can use any preferable environment you want. And Please work at your own pace. If you get stuck, please remember that we have Discord and all the community is here there for you. All right. Thank you for listening. And after the hands-on work, we'll have another session on DiVincenzo criteria. Okay.
So we'll start the final why. So please download the book. You download it.
Bean, what time do you think should I start for the second session?
So how many time? 30 minutes. Is it fine for you?
Yeah, I think it's okay.
So let's proceed. Fichier soit enregistré en dossier en entier. Je vais déjà C'est fou. Ça c'est la deuxième partie. Il va présenter dans 30 minutes. De détails. Je vais commencer avec tous ces packages. Et sur votre machine, là, ils sont installés sur Google Colab. Oui, ils ne sont pas installés sur votre physique machine. Donc, du coup, vous avez besoin. Ils sont installés. Et du coup, là, vous pouvez commencer à créer des qubits, des polygates, ce que vous venez d'apprendre. Après, pour commencer, c'est la réponse. C'est très simple. C'est créer les opérations. C'est le basics. Tout ce que vous voulez. Comment créer des qubits et aussi créer des qubits et le peuple visualiser des états. Voilà. Après, parce que le hardware, en fait, c'est impossible de créer des qubits intriqués en réalité. Très difficile. Donc, souvent, il y a certains qubits qui se connectent avec l'autre, pas avec l'autre. Ouais, comme IBM qui crée General. C'est une choisir une meilleure option pour vous. n qubit qui connecte avec n. Et ce qui est largeur de notre circuit parce que vous elle est présente si vous manipulez les planètes qubits, votre information perd. Voilà, et du coup, ils sont tous faire. Et du coup, c'est juste pour montrer en réalité à partir des équations sur la machine comment on le fait physiquement. On pourrait continuer avec vous. Donc là, c'est très beaucoup de choses. A réussi à faire les tout. C'est ce que les statistiques en tout cas. Je sais pas si c'est bien ou bien pas. Difficile de savoir, mais on ramène tout. Donc, en fait, le premier choix, ça va être les bases. Commencer par les bases du matin. Ensuite, c'est l'après-midi, c'est important aussi, c'est quantum variation algorithm. C'est l'algorithme qui permet de faire moi, maintenant, il y a des applications académiques. Applications académiques utiliser cet algorithme dans votre domaine, par exemple, à MIT. Ouais, algorithme qu'on va apprendre aujourd'hui, pour montrer que ça marche. Voilà. Donc, on va commencer très très. Ouais, si vous voulez, vous pouvez poser. Moi, je peux pas contrôler les gens qui viennent.
Il y avait quand même des gens.
Normalement, là, parce que là, ce matin, on a plus que 200. Ce matin, on a un problème en ligne, plus 9 du matin.
Oui.
En fait, on va faire, moi j'ai tout calculé. Par exemple, il y a fait 2 heures de practice. Et je vais continuer pour rattraper les autres. Mais il n'y a pas qui était. Et jusque-là, il y a des gens qui ne viennent pas à la séminaire. Il y a des gens qui viennent. Demain, il va y avoir des gens qui viennent en 8. Et aussi, et je veux vous inviter.
You, yes,
So then,
you're a beginner. Practice beginner.
yeah, which one?
The first one. Oh, okay.
It's just full matrix function.
Two matrix. Okay. Yes, we need
Is everything is okay?
everything quite clear, but I don't know how to
Create a qubit.
now create a state one.
The stigma. From 0.
So you educate myself.
So QC, we better like quantum circuit. And then normally it's something like say 0 by random. And then we need to add it may mean you will implement it to so we start from 0 because it's Python.
But you have the here.
No, it's 0. 0. Because on the index in Python start from 0.
Okay.
See, here is mean you create one qubit. You see, and a qubit by default start by 0 state. And yeah, you just say that you want to create, you want to implement Qiskit on the qubit 0. Okay.
The Qiskit, the function. Why do you put 0 in the function?
No, it's
No,
not.
it's not a function.
It's not a function.
Matrix. Matrix and 0 is the first column.
It's going to be easy to see. So if you do,
De l'autre côté.
Ah, c'est il y a le.
so on Qiskit, when you say use E, it means quantum circuit, right? 0, R1. Okay, so that is the name of your quantum circuit. That is the function. Okay, this function is you store the quantum circuit on this parameter, and here that is 1. 1 is the number qubits that you want to create. So here you just mention 1. So you want to create 1 qubit. Okay, and initially the qubit is stay 0. So you just create the qubit 0.
Good.
You understand? So you just by doing that, you just create a quantum circuit with the qubit 0. And then the question is, you want to create a qubit 1 in the end. Okay? And when you want to create a qubit 1, you just need to add the X gate. The X gate means you will flip the qubit from 0 to 1.
I know the quantum circuit part, and that would need help when I go to the transmigration and optimization, I think.
Yeah. So if you need any help, please come in.
Yeah.
Do you understand the what we need to transfer the circuit for tonight?
Yes, it's somewhat noisy. Mitigation.
Yes.
Yes, it's just like this.
Okay. So because when you create your system, right? for example, in a hardware, the qubit cannot connect perfectly one from the other because we connect the qubit manually. For example, if you have a system, IBM system, we have the system, for example, 10 qubit, and they won't connect to each other, right? Like this. But for example, for the qubit one, will not connect with the qubit right here. The last one. See, this one and this one will not connect. This one and this one will not connect. Or they will connect, but they are not next to each other. See? So sometimes, for example, when you create a quantum circuit, the system will not proceed well. Because when you run on a real hardware, you need to implement something that your hardware understand and better proceed. So that's why they created transpile your data into qubit that they are physically next to each other. And optimization is mean because they are not next to each other. And when you transpile it, you will increase the depth of the circuit. For example, if you want to do a CNOT, you may have to do like 3 swap ways. So swap way is very expensive, so it's longer. So the idea you have to use like optimization, and in this case they will charge the quantum depth, this depth, and this case more suitable one from the hardware.
Optimization level has only 3 settings.
Exactly. So
Setting or a parameter?
that is a parameter.
Okay.
They have a 3 level of optimization. Later, if you want to go beyond, they have many other type of optimization. AIs, they implement AIs 150 as well. Try to use it, but it really depends on your problem. Because sometimes you use the highest level of optimization. For example, your system are very complex, so the optimization will use like stochastic but so if your problem is very complex in this case, it will take very, very long time to optimize it. So that's why IBM implement AI as well in order to speed up. There are many more if you want to go beyond.
Okay, but does it depend upon the number of qubits? Like more qubits you use?
Yes, it depends on the number of qubits because the time costing. If you have many qubits, it means you will have many more options. Because stochastic, it means you have to create one possible circuit in order to select the one who has the least case, for example. See, but in this case, you have to run for all possible options. It's costly. So if you have many qubits, means that your simulation will become cumbersome because that is a combination of many qubits. So that is the thing. But for now, for the exam, you have just few qubits, and you can use you can test on the option of on the level of optimization to see the quantum circuit will change. Do you need some time? You want to run on your local machine?
Yeah, because I have struggled doing the content here. So you want?
Do you have a Google Drive?
No, I don't. No, I'm just starting with this.
Because it's not prepared for running a local machine. That is a GitHub, so please, can you open a Google Drive? It's really, do you have, so Gmail is the Google, right?
Gmail, yeah.
So you can open Google Drive and then have this. Yes. On the website, maybe on Safari or any every come in and connect with your email. Okay. So please come to the GitHub and download the GitHub. Yes, and download this. That is a Jupyter notebook. First, if you want to run it, you have to use Anaconda too, so you understand. So now you come to Google Drive and upload the data. Okay. And, yes, exactly. Getting started. Qiskit for a minute. Okay. Okay, no, it's not.
That was not. Okay. All right. So
Where is
on the video.
Just I Google Colab. This one and go. Very quickly and just continue. Now you get everything. Just okay. Okay, and close. Now you open. No, just open. Just click. Then it works. And then you don't need to install anything on your local machine. Okay. Alright. And to run on Google Colab, you have to first install everything. Here, just run it. Yes, and because you have your own system on the Google Drive, and when you run it, this so you manually try to install all of this on your system. Yeah. And then the idea of Google Colab that they will adapt your system the next one. You see, so it's very powerful. So anything like that. Yeah. I see. Okay. So you have also the solution, because the beginning you may need the solution. Because the beginning, yes. So you may need the solution in the beginning to understand how it works. Jim qui est présent ou pas? On fait directement les Madame, son vote. Ça va. Ça va faire 1h30 de transport, ça va. Ah, 1h30. Ouais. Ouais. Si. Tu le supportes là. Merci. Ouais. Allez, qu'est-ce que je peux t'aider? Bah là, j'ai pas installé Python, donc. Non, t'as même pas besoin d'installer. Non, non. Ah non, non, non. Ah, c'est pour ça. Non, t'as même pas besoin. Ah oui, tu peux passer Python aussi, là. Ouais. Oui, c'est bon. Donc, c'est plus facile. Alors, bien, je vais te montrer. T'as Google Drive? Vas-y. Ouais. Voici ta Google Drive. Voilà, tu as tout là. Tu vois, du coup, tu vas télécharger ce fichier. Après, tu as juste besoin de le mettre et ça va marcher tout seul. Pas besoin de rien installer. Ça va marcher tout seul. Donc, tu peux faire aussi, surtout à AI ou tout, tu n'as rien besoin d'installer. Donc là, et si tu dois installer, parce que ça, sur Google Drive, tu as ton propre environnement. Pour un environnement, c'est bien sur Google, c'est possible d'adapter en fonction de ce que tu le demandes. C'est pour ça, en fait, tu peux installer sur ton truc. Et en fait, le système va héberger tout seul. Hello, everybody. Everything is good? Do you need some help? People on online? You studying my Jupyter? Ah, do you install everything in your local machines or do you use Google Colab? We advise you to use a Google Colab. Ah, so that is yes. So we prepare everything on Google Colab, and you don't need to install anything in your local machines. That is the power of Google Colab. So just go to Google Drive. And then at the, you can see in the end, is there another link? For Journey, no, you don't need to install. If you use your local machines, we advise you to install everything in Alakunda environment. But for the exercise, we create everything in Google Colab. So please go to Google Colab, and then you don't need to install anything by yourself. Yeah, well,
All right, Bean.
Yes.
Yes, I think I've handled some. We can start for the next session if everything's fine.
Yes, please share the screen. Right.
Okay, welcome back, everyone. If you haven't finished your first exercise, I think Bean helped very well on site. You could keep your notebook and can continue from where you are in the future. And please feel free to ask the questions. I'll be active through the Discord. Okay. Now we'll move on to session 2, which is the DiVincenzo Criteria Lab. This session bridges like fundamental physics and practical implementation. In it, we'll explore the minimum requirements that any physical system must satisfy to perform quantum computation. Okay, so what exactly are the DiVincenzo criteria? Well, in years of 2000, physicist David DiVincenzo asked a quite deceptively simple question. He asked, what does it actually take to build a working quantum computer? And his answer became a practical checklist, specifically the minimum physical requirements that every quantum computing platform must satisfy to be viable. But what makes this criteria so powerful is that their lasting relevance. Over 2 decades later, hardware teams still use them to guide quantum architecture development. So like for every advance you read about, things like improved coherence times, better gate fidelities, or like getting higher qubit counts is directly addressing one or more of these requirements. So understanding these criteria helps you evaluate real quantum computing platforms and the trade-offs they face. Okay. DiVincenzo identified 5 essential requirements, as you see on the slide. Let me walk you through each one. So first up is scalability, which means that this means we need well-characterized qubits in a system they can grow. And this isn't just about making more qubits, it's about maintaining precise control over individual qubits and their interactions with predictable behavior as the system scales. So the challenge is keeping quantum coherence while increasing system complexity. Now here we have second, we have initialization, which is the ability to reliably set qubits to a known starting state, typically the all-zero state. This is crucial because every quantum algorithm assumes you're starting from a clean and well-defined state. So without reliable initialization, there will be accumulated errors from previous computations, and it would contaminate your results. And third here, we have on the list is long coherence times. In simple terms, this means the qubits must stay quantum longer than gate operation take. Specifically, the decoherence times, known as T1 and T2, must be substantially longer than the time needed to execute quantum gates. This ratio determines your computational depth, and in other words, how many gates you can apply before quantum information is lost to the environment. And fourth here, we have universal gates. This requires a small native gate set that can express any quantum algorithm. Well, but mathematically, this means the hardware must support operations sufficient to perform arbitrary unitary transformations. And this is analogous to how negative AND gates are universal for classical computation, but the quantum version must preserve superposition and entanglement. And fifth, we have measurement, which is the ability to read out each qubit individually and accurately. This is where quantum information collapses into classical information that we can interpret. The measurement must be strong enough to reliably distinguish the 0 state from the 1 state with high fidelity and minimal disturbance to other qubits. Now let's see how these criteria translate into our hands-on practice, starting from scalability. In the notebook here, you'll build a gigahertz state, first on 3 qubits and then on 5 qubits. You'll compare ideal simulations against noisy ones. What I mean by ideal is you're using the AER simulator again, and the noise simulation, for the noise simulation, we will use these fake backends, okay? So this demonstrates a fundamental challenge, namely that quantum correlations become harder to maintain as system size grows. Each additional qubit introduces new error channels, and the hardware topology directly affects how well entanglement works across the system. So here's basically what you'll observe. In an ideal simulation, you'll see only the all zeros and all one states appearing with a clean 50-50 split. But in a noisy simulation case, which is corresponding to the real hardware, those peaks shrink and many other bit strings appear. You'll find the fidelity decreases as qubit count increases. This right here is the scaling challenge that every quantum platform faces. Now moving to the second criterion, we have initialization. You'll practice using the reset instruction to return qubits to the 0 state, and the initialize method to prepare specific quantum states. This includes everything from simple computational basis states like 0 and 1, and all the way to superposition states and even entangled Bell states. You'll also explore mid-circuit resets for qubit reuse. Okay, so then why does this matter? Well, starting with the clean known state is critical for quantum error correction. It enables iterative algorithms and stabilizer circuits, and it reduces ancilla qubit requirements. The distinction between hardware-level coding and algorithmic reset is important. Ultimately, fast, reliable initialization extends your effective computation time in noisy systems because basically you spend less time preparing states and more time actually computing. Now the third criterion addresses one of the quantum computing's fundamental challenges, and that is decoherence. In this exercise, you'll run a T1 decay experiment using the fake Figo backend. You prepare a qubit in the excited state 1, add delays of varying length, and then measure. This is essentially a race between computation and the coherence. You observe T1 relaxation directly, which is how quickly the excited state 1 decays back to the ground state 0. The probability follows an exponential decay curve. It starts at 1 and drops to about 0.37 at a time to equal to T1, and eventually approaches 0. So here's the critical insight. Gate operations take around 10 to 100 nanoseconds, while T1 times on fake Vigo are around 50 to 100 microseconds. De Vincenzo's rule requires that T1 be much longer than the gate time. Without long coherence, quantum information is lost before computation completes. So this is basically why improving coherence time is one of the most critical goals in quantum hardware development. Now we have criteria 4 and 5 addresses the operations we can perform and how we read results. For gate universally, you'll see how Qiskit decomposes a complex Toffoli gate here, also called CCX, into the native basis case of IBM hardware, which are RZ and SX and ECR. This demonstrates that a small set of native gates can express any quantum operation. The decomposition might look complicated, but it proves that the available gate set is computationally universal. Now for the measurement, you'll simulate readout errors by giving each qubit a 2% chance of being measured incorrectly. This mirrors a real device behavior. Every real quantum computer has readout errors, and this exercise shows why measurement fidelity matters and motivates readout error mitigation techniques that help recover true results from noisy measurements. So now let me explain how this lab is structured. For each of the 5 criteria, you'll follow a 3-step pattern. First, you'll find a brief explanation of the physics concept. Then you work through a code exercise, filling in missing code to demonstrate that criterion using Qiskit. And finally, you run the code and observe the results, and analyzing outputs and comparing ideal versus the noisy behavior. You work with 3 fake backends. There are fake Brisbane with 127 qubits, and fake Vigo with 5 qubits and specific T1 characteristic, and fake Sherbrooke with 127 qubits, but with a different topology. These aren't just the random simulators. They're like built from real IBM quantum computer calibration data. So it provides realistic noise models with authentic error rates and connectivity constraints and coherence times. But they can run locally with 0 Q time, so it will give you the reproducibility to it and immediate iteration for this learning environment. The tool you'll use include the sampler for running circuits and getting measurement results, AR simulator for high-performance simulation with noise models, the transpower function to adapt circuits to hardware constraints, and the noise model for creating and applying custom error models. So before you begin, please let me emphasize why this matters. So the key takeaway is every hardware advancement in quantum computing targets one or more of these De Vincenzo criteria. So when you read about improved coherence times or lower gate errors in research papers or company announcements, you're seeing these principles in action, right? And these aren't just the historical requirements, they're the active challenges defining the field right now. And understanding these criteria also explains why quantum computers have the architectures they do. The trade-offs between these requirements drive fundamental design decisions in platforms like IBM Quantum, and Google Sycamore, and trapped ion systems. Each platform makes different choices about which criteria to optimize and which trade-offs to accept. So please, let's get started. You can find the Jupyter notebook for this session named DiviSensor Criteria Lab on the very same file. And there will be a bonus activity on the final exercise. It's optional, but it's a quantum teleportation module to explore quantum communication criteria. So, okay, that's it. Thank you very much.
Thank you, Jim. So I think we will take like 15 minutes more to practice, and then we can wrap up for the morning section. If you have any questions, please ask on the Discord, and then we can answer shortly on the question if you have. Don't worry.
Yes, I do. Yeah.
Yeah, okay. But, so hello everybody. People on site are a little bit hungry. So we think that we would like to go for lunch. You can stay and see you in 1 hour. The Zoom is remaining, so no worry about that. You can stay on the Zoom, and in your country, please keep working. And if there are any questions, please ask us on the Discord. And see you later. You have free lunch for us. But during the hand-on notebooks, if you want to take a break, you can take a break. You need to stay and freedom to do. Just stay.
Do you like what food options are there around here?
We go together in the downstairs. You don't need. You want to do Ramadan?
No, it's intermittent fasting. Like
Right. We can go down for lunch. Where do you want to go? I think like we share someone's upstairs. Here, the library. So I will stay on the top. Are you staying? Don't worry, there are